Can you hear me?
Yes, sir.
Yes, sir.
Okay. So last time we studied about the structure of hemoglobin. So today actually we will study about the structure and function relationship of the hemoglobin. So what structure imparts the characteristics of hemoglobin? That is very important. Which structural characteristics impart the functional property? Okay, which structural characteristics imparts the functional characteristics of the hemoglobin is very important to understand and to know, because as we know we have a 5 finger attached to a big palm in our hand that enable us to hold many objects tightly, isn't it? So we can perform many activities very easily due to our structural features of our hands and limbs. So this is similar to the hemoglobin also. So for hemoglobin also the hemoglobin function better because of its structural characteristics. So that we are going to study today. Last time we also studied about the heme synthesis and regulation of heme synthesis. We know that delta amino levulinic acid is the rate limiting enzyme during the heme synthesis, and these enzymes are inhibited by free heme and activated by the presence of globulin. Similarly, it is activated by the presence of ferrous iron, and copper is the stimulator that helps to initiate this pathway. Similarly, I forgot to mention one thing lastly, the last enzyme of this heme synthesis pathway, that is ferrochelatase, is the enzyme that can be inhibited in the presence of a high level of heavy metals. If there is a presence of heavy metal like mercury and another arsenics and other compound, that may inhibit this ferrochelatase, leading to the blockage of the heme synthesis pathway. That also leads to the formation and accumulation of precursor molecule like porphobilinogen and porphyrins that results in porphyria. Okay, in the next class we will definitely study about the porphyria. So porphyria we need to learn. Today we're just going to study about the structure and function relationship of the hemoglobin. Okay, and in the next class we will do about the porphyria. Okay, now the structure function relationship. Okay, so already we knew that the tertiary structure of hemoglobin and quaternary structure of hemoglobin is the main important structural features that imparts the binding of heme molecule in the pocket of the hemoglobin, and due to the six valency of the iron, it can bind with 4 pyrrole ring, and then 5th to the globin molecule and 6th to the oxygen molecule. This is what we have studied till now. And so when fully saturated, each gram of hemoglobin can bind to 1.34 ml of oxygen, and the degree of saturation is related to the oxygen tension, which normally ranges from 100 millimeter of mercury in arterial blood to about 35 millimeter of mercury in the vein. So you see that arterial blood are highly saturated with the oxygen, right? Okay. So you can see that already we learned that alpha beta dimer is there. There is a strong covalent bond between alpha beta dimer, and with the two alpha beta dimer there is a weak ionic bond like hydrogen bond or another ionic bond, which is less stable. So due to this less stability, the hemoglobin molecule can change its conformation. Conformational change will be done during the oxygenation and deoxygenation process. There will be the conformational changes because of this weak ionic and hydrogen bond present in between two alpha beta dimer. You can see in the images at the left side of your slide, there is one alpha beta dimer here in the top and second alpha beta dimer in the lower position. And there is a strong covalent bond between this alpha beta dimer and weak ionic bond and hydrogen bond between these dimer. Okay, so during oxygen, it changes the conformation. Ionic bond further breaks and oxygen can bind to this hemoglobin molecule. Okay, so the hemoglobin tetramer is composed of two identical dimer, alpha beta 1 and alpha beta 2. Two polypeptide chain within each dimer are tightly held together by the hydrophobic interaction. In contrast, the two dimers are able to move with respect to each other, being held together by primarily by ionic and hydrogen bond. Okay, so the weaker interaction between these mobile dimer result in the two dimer occupying different relative position in deoxyhemoglobin as compared to the oxyhemoglobin. You see here, this is a deoxyhemoglobin form. The structure is little bit different in compared to the oxyhemoglobin form structure. You see the both alpha beta dimer move apart during the oxygenation form. Some ionic and hydrogen bond between alpha beta dimer are broken in the oxygenated state. So the strong interaction primarily hydrophobic alpha beta chain from the stable dimer, so this cannot be changed. So this deoxygenated form is called T form or taut structure of DMO, tense form. This is known as a tense form because this is not oxygenated, this is a tense form. And because of this ionic bond which is present in between these two dimer. And when there is an oxygenation, the ionic bond between these two dimers breaks and it expands. Actually, the hemoglobin molecule expands during oxygenation. And this expansion is also known as a relaxed form, R form. Oxygenated form is R form. Deoxygenated form is T form. Okay, relaxed or R form, T or taut form, or also known as a tense form. Okay, so the T tense form, deoxy form, and low oxygen affinity form. T is the low oxygen affinity form. It means that this hemoglobin molecule has lesser affinity to our oxygen. Due to this reason, when it uploads oxygen to the tissue, it do not carry back oxygen. Okay, if it has a high oxygen affinity, it oxygen to the tissue. At the meantime, it also take back oxygen from the tissue. So to prevent this, this structure has a lesser affinity towards oxygen. And the R form, where is known as a relaxed form, has a very high affinity towards oxygen. It means that when it binds to the oxygen, it holds it tightly. This actually occurs in the liver. In the liver, where there is a high saturation of oxygen, what happens that this hemoglobin changes its structure due to the breakage of this ionic bond, and due to this conformational changes, it increases the affinity towards oxygen. So the oxygen can bind easily with this hemoglobin, okay, so that it can transfer oxygen from the lungs to the other tissues. This is the very important mechanism why hemoglobin in the liver, in the lungs can hold oxygen, and why the hemoglobin in the tissue can upload oxygen, okay, due to the characteristic change of the hemoglobin molecule. Okay, let's see further. The binding of first oxygen molecule to the T form, tense form, leads to local conformational change that weakens the association between the subunit forming the R. So you see when one molecule of oxygen first binds to the one subunit of the hemoglobin, then the conformational change starts, conformational of the structural chain now initiates, starts, that results in the increase in the oxygen affinities toward the other subunit of the hemoglobin. Okay, so that results in more increase, step by step increase of oxygen affinity towards the remaining subunit of the hemoglobin. Okay, let's see in this picture again. So this is an ionic strong hydrophobic bond, and this is an ionic bond between the two pair, and this is a tense form. Tense form. Each subunit resembles myoglobin tertiary structure, and when oxygen binds to one subunit of this hemoglobin, the conformational change now starts, weakening the ionic bond, and the ionic bonds are weakened and broken down, and that increase the oxygen affinity towards the other remaining subunit of the hemoglobin. Okay, one oxygen binds hemoglobin subunit, oxygen binds, disturbs the internal dimer bonds, and that increases the oxygen affinity of the remaining subunit. Okay, so when the oxygen affinity is increased, it can hold, or it can bind with the oxygen very quickly and very easily, quickly and very efficiently, easily it binds to the oxygen in the lungs. Okay, so the myoglobin can bind only one molecule of oxygen, although the structure of myoglobin is almost similar to the hemoglobin. Myoglobin is a single monomeric unit, whereas a hemoglobin is a quaternary structure. You all know that. Otherwise, the myoglobin also contains the same heme molecule and a globin molecule. So myoglobin is also almost similar. But myoglobin can bind only one molecule because of a single iron atom or single heme atom and heme molecule at the center, whereas hemoglobin has a four, so it can bind four oxygen molecules, and the oxygen binding is cooperative. So oxygen binding nature of the hemoglobin is cooperative. Okay, because of the nature of oxygen binding that we just explained in another previous slide. As each oxygen binds to the hemoglobin, the molecule undergoes a conformational change, increasing the oxygen affinity for the remaining subunit. This creates the sigmoidal oxygen dissociation curve. This creates the sigmoidal oxygen dissociation curve, or S-shaped saturation curve of hemoglobin. So what is the shape of the oxygen dissociation curve? The shape of oxygen dissociation curve is sigmoidal because of the cooperative binding of oxygen. It means that cooperative binding of oxygen can be explained by the things that when one molecule of oxygen binds to one subunit of hemoglobin, the oxygen affinity towards the remaining subunit of hemoglobin increases. Okay, so initially slow binding of oxygen will increase rapidly after some time. So this is a cooperative binding, and that creates the sigmoidal oxygen dissociation curve. Thus, the relation between oxygen tension and hemoglobin oxygen saturation is described by the oxygen dissociation curve of the hemoglobin. Okay, so I will show you what is oxygen dissociation curve. Okay, what happens to my slide? Okay, so you see this is the oxygen dissociation curve. Okay, the curve for myoglobin and hemoglobin, so important differences because myoglobin is a single molecule, so it is not sigmoidal, it is parabolic, whereas the oxygen is sigmoidal. Myoglobin has a higher oxygen affinity than does the hemoglobin. The partial pressure needed to achieve 50% saturation is approximately 1 millimeter Hg for myoglobin and 26 millimeter for mercury for hemoglobin. So hemoglobin needs more oxygen for saturation, whereas myoglobin needs lesser oxygen for saturation. Okay, so you see this is the partial pressure of oxygen in the tissue that can still binds with the oxygen, whereas this is partial pressure for the hemoglobin that needs higher oxygen for saturation at the lungs. Okay, so this is oxygen dissociation. Oxygen dissociation curve of hemoglobin dips at the oxygen concentration that occurs in the tissues. This permits oxygen delivery to respond to small changes in the partial pressure of oxygen. The oxygen dissociation curve for myoglobin has a hyperbolic shape. Already you have seen in the diagram. So note, myoglobin is designed to bind oxygen released by the hemoglobin at the lower tension of oxygen in the muscle, whereas myoglobin releases oxygen within the muscle cell in response to the oxygen demand. But in contrast, hemoglobin dissociation curve is sigmoidal. It means the binding of oxygen molecule at one heme group increases the oxygen affinity of the remaining heme group in the same hemoglobin molecule. That is heme-heme interaction. That is known as a heme-heme interaction. The affinity of hemoglobin for the last oxygen bound is 300 times greater than the affinity for the first oxygen bound. So it means when at the beginning, when one molecule of oxygen binds to the hemoglobin, the affinity is very low. But when the last molecule of oxygen binds to the fourth subunit of hemoglobin, the oxygen binding capacity increases more than 300 times. Okay. So what are the allosteric effector affecting oxygen binding affinity of the hemoglobin? This is a very, very important question that is always asked in the physiology or also in the biochemistry or even in the medicine when you study medicine and critical care, anesthesia. This question is very important. So this knowledge will help you to learn medicine and also the anesthesia or critical care in the future. So you see, just a moment, can I pick up the phone? So, so the allosteric effector affecting oxygen affinity are heme. Then please move the window away from the syrup, please. No, I don't know what is this. And the effector of 2,3-bisphosphoglycerate on oxygen affinity. These are the three allosteric effector of oxygen binding affinity. So these are collectively called allosteric because allosteric, it binds to the other side. Okay, so because the interaction at one site on the hemoglobin molecule affect the binding of oxygen to the heme group at the other location, this is known as a allosteric effectors, allosteric effector of the, okay. Loading and unloading of the oxygen is described by the heme-heme interaction. Okay, so the loading in the lungs, oxygen is high and hemoglobin becomes saturated or loaded with oxygen in the lungs. In the peripheral tissue, in contrast, you see oxygen concentration is low, so the oxygen is uploaded or unloaded by the hemoglobin at the tissue level. So that is how the oxygen is carried from the lungs to the tissue. And the change in oxygen affinity with the pH in the local tissue also helps in the oxygen unloading of the hemoglobin to the tissue. If you see that due to the metabolism, lactic acids and pyruvic acids and other organic acids are being produced continuously in the tissue. So in the tissue, the local pH is very, very low. And due to the low pH, what happens? The oxygen dissociation curve always shift to the right. So due to it means that oxygen is easily uploaded in the low pH. So this phenomenon is known as a Bohr. This phenomenon is known as a Bohr effect. Okay, so the hemoglobin oxygen affinity is reduced as the acidity is increased in the local tissue. Since the tissue are relatively rich in carbon dioxide, the pH is lower in the arterial blood. Therefore, the Bohr effect facilitates transfer of oxygen. This is known as an allosteric effect of pH or allosteric effect of acidity in the oxygen dissociation curve. Okay, similarly, rising pH or decrease in carbon dioxide result in greater affinity. So if you see in the lungs what happens, there is a increased concentration of bicarbonate, and this bicarbonate imparts the alkalinity, or it decreases the, or it increases the pH of the blood at the lungs. Due to this, the oxygen binding affinity is increased in the lungs. Okay. So the pH is one of the very important effectors. So you see that there will be the right shift of the oxygen dissociation curve when there is a low pH, and there is a left shift of the oxygen dissociation curve at a high pH. Normal blood pH is around 7.4 plus minus 0.2. So you see that if there is a pH of 7.6 that is in the lungs, the oxygen dissociation curve shift to the left. This is shift to the left. It means that it has a this at this point the hemoglobin has a higher affinity towards the oxygen, so it binds or it holds oxygen very tightly in the lungs. Okay, and if you see in contrast in the tissue, the local pH is very low because of the carbonic acid and other organic acid. The pH is low. In this condition, the hemoglobin loses its affinity towards oxygen. So it loses the affinity. So it means the oxygen is easily dissociated from the hemoglobin at the tissue level, and oxygen is delivered to the tissue. So this is the effect of pH on oxygen dissociation curve, or this is the allosteric effect. Okay, left shift and right shift due to the pH. Another important allosteric effect is 2,3-diphosphoglycerate. 2,3-diphosphoglycerate or bisphosphoglycerate is produced during the glycolysis pathway, which is actually not exact glycolytic pathway. It is a Rappaport-Lewering pathway, or also known as a Rappaport-Lewering shunt pathway. Shunt pathway is the side pathway or the extra pathway that originates from some main pathway. For example, this is a glycolytic pathway, and when through the same glycolytic pathway, you can see 1,3-diphosphoglycerate is converted to 2,3-diphosphoglycerate, and this compound can generate again 3-phosphoglycerate to enter glycolytic pathway, or this compound is used as a some substance in other important mechanism. For example, this 2,3-bisphosphoglycerate produced from this Rappaport-Lewering shunt pathway from the glycolysis is a very important allosteric effector of the oxygen dissociation curve. Okay, very strong and important allosteric effector. Okay, how I will explain you right now. The proportion of this pathway appear to be related to the large cellular ADP and ADP level. When ATP falls and ADP rise, a greater proportion of 1,3-DPG is converted to the ATP producing state. But when the ATP level is high, more amount of 2,3-bisphosphoglycerate is produced. This mechanism source ratio supply of ATP meets cellular need. In the same or in by the same mechanism, this molecule also ensure the safe delivery of oxygen to the tissue. In the deoxygenated state, you see the hemoglobin, adult hemoglobin can bind this 2,3-BPG at the ratio of 1:1. It means that one hemoglobin molecule can bind one molecule of this 2,3-BPG. Okay, and after binding this 2,3-BPG, it reduces the oxygen affinity and improve oxygen delivery to the tissue. Okay, so this is a very interesting and amazing phenomena. You see, when our tissue is in high need of oxygen or high need of energy. So for high need of energy also tissue requires oxygen. So what happens, this 2,3-BPG will bind to the oxygen, hemoglobin, and this hemoglobin loses its affinity towards oxygen, so that more amount of oxygen is delivered to the tissue very easily. So when oxygen is unloaded by the hemoglobin molecule and 2,3-BPG is bound, the molecule undergoes a conformational changes. So it can also change the structure of hemoglobin. Okay, to T form, the resultant molecule has a lower affinity for the oxygen. As the partial pressure of oxygen increases, the 2,3-BPG is now expelled out from the hemoglobin, and it resumes its original relaxed form, and this relaxed form has a higher affinity towards the oxygen. So in this image, I will explain you very easily, and you can see it very clearly. This is what is this? This is a relaxed form, or R form of the hemoglobin, where oxygen has been bound to the hemoglobin, where the oxygen affinity towards oxygen has been increased temporarily. So, and when it moves to the tissue, you see there is no 2,3-BPG, but when it moves to the tissue what happens? This 2,3-BPG binds with the hemoglobin molecule. Binding of this 2,3-BPG or DPG change the structure of hemoglobin from R to the tens. So when it changes the structure of hemoglobin from R to tens, this hemoglobin molecule loses the affinity towards oxygen, and then it releases the oxygen very easily to the tissue. Okay, so this is very important mechanism. Number of situations associated with hypoxemia, like when you go to the high altitude, or when there is a pulmonary or cardiac disease, or when there is anemia due to blood loss, what happens? The level of 2,3-BPG level in the RBC increases. So when the level of RBC, 2,3-BPG in the RBC increases, it can easily lose the affinity of the oxygen. So it can, very less amount of RBC or very less amount of hemoglobin can also transport oxygen very easily towards the tissue. So when you go to the altitude, or if you see the level of 2,3-BPG is very high in the people living in the mountain area or the hilly area, compared to the people living in the dry area or the plain land. Okay, so increased 2,3-BPG also plays a role in adaptation to exercise. The people who do a lot of aerobic exercises has also high level of this compound in the RBC. Okay, so it's not essential to life, but normally when there is a genetic disease or some problem that leads to decreased synthesis of 2,3-BPG, our body adapts by increasing the number of RBC. To compensate the deficiency of 2,3-BPG, what our body does? Our body produces more RBC. Okay, so the increased oxygen affinity to the fetal hemoglobin also is related with the 2,3-BPG, because this 2,3-BPG is very high in the fetus also. Okay, the increased oxygen affinity of stored blood is accounted by the reduced level of 2,3-BPG. So now, what are the factors that causes the oxygen dissociation curve to shift toward right, or what are the factors that causes the oxygen dissociation curve toward the left, is very important to understand. Okay, so this will be a very important question from the examination point of view. So I think you should remember this point. You see, already we have talked about the 2,3-BPG and the pH. Okay, so the right shift is due to 2,3-BPG, high hydrogen ion concentration, high carbon dioxide, and high this sickle cell hemoglobin. Sickling hemoglobin also shift towards right. It means it delivers oxygen very easily, and the left shift or is due to 2,3-BPG and fetal hemoglobin. Okay, is the left shift. So pH, carbon dioxide, low pH, carbon dioxide, 2,3-BPG, and even temperature. When there is a fever, that time also oxygen delivery to tissue is increased, because our tissue requires more oxygen that time. So all these condition favors easy release of oxygen to the tissue. That is described as a right shift of oxygen dissociation curve. Right shift of oxygen dissociation curve. Similarly, the left shift of oxygen dissociation curve is due to increased fetal hemoglobin, increased carbon dioxide, and increased pH. Okay, increased pH leads to the left shift. So that's all. Keeping this slide at the end, I would like to you to ask me question if you have any problem, or if you do not understand some points, I will be happy to explain it to you, because this is a very important lecture. Otherwise, I have finished my class for today. I left this class, very little class, small class for today, because I want you to learn slowly and understand better. So that's why I did not complete the class in my last lecture. Otherwise, I would have completed this lecture in the last class. Okay, so this is important. So I break the classes to the two lectures.
सर त्यो एलोस्टेरिक वाला थियो नि त्यो एकचोटि फेरि एक्सप्लेन गरिदिनु न
एलोस्टेरिक वाला एलोस्टेरिक भनेको चाहिँ त्यो इन्जाइममा पनि एलोस्टेरिक इन्जाइम भनिन्छ नि हैन एलोस्टेरिक इन्जाइम भनेको चाहिँ के हुन्छ भने when it binds to the one some different portion, and then it changes the conformation and increase the affinity or decrease the affinity, त्यसलाई एलोस्टेरिक भन्छ। अब एलोस्टेरिक इफेक्टरहरू के हो भनेर सोध्यो भने हेमोग्लोबिन डिसोसिएसन कर्वको अथवा हेमोग्लोबिनमा बाइन्डिङको एलोस्टेरिक इफेक्टरहरू के हो भने तीनटा कुरा आउँछ। एउटा हिमिम इन्टरेक्सन। हिमिम इन्टरेक्सन भनेको चाहिँ त्यो अक्सिजनको कोअपरेटिभ बाइन्डिङ हो। अक्सिजन कोअपरेटिभ बाइन्डिङ अफ अक्सिजन भनेको इट इज एक्सप्लेन बाय द हिमिम इन्टरेक्सन। इट मिन्स दैट व्हेन one molecule of oxygen binds to the heme, I will show you the slide again and then explain it. Okay, these three things I have to show you. Heme interaction means when one molecule of oxygen binds to one subunit of hemoglobin, then there will be a conformational changes. Conformational changes is the breaking of the ionic bond between alpha beta dimer, and that causes the change from T state of hemoglobin to R state. Okay, when there is a change in the R state, the oxygen binding automatically increase very high in the magnitude of doubling and like that. So I have explained you like when oxygen bind to the first unit, if you compare the oxygen binding of hemoglobin to first unit with the last unit, the affinity is increased up to 300 times. So so this is a heme interaction or cooperative binding of oxygen. Due to this cooperative binding, the hemoglobin dissociation curve or saturation curve is always sigmoidal. Whereas if you see the oxygen binding curve of this myoglobin is parabolic or hyperbolic. Okay, so this is heme interaction. And another one is Bohr's effect. Bohr effect is due to the pH, low pH, especially increased carbon dioxide in the tissue causes the pH to decrease, and this low pH also causes the conformational changes. So what conformational changes it creates is it converts the relaxed R form to the it converts the T form to the R form of the hemoglobin, so that oxygen is readily uploaded or released from the hemoglobin to the tissue. And similarly, the 2,3-bisphosphoglycerate, which is a byproduct of this glycolytic pathway, this also binds with the hemoglobin molecule at the center pocket, and that causes the conformational changes of the hemoglobin molecule due to the change in the structure of RBC from the R to the T. Again, the oxygen uploading will be very easy. I know, so oxygen will be very easily released from the hemoglobin. So these are the three allosteric effector that also explain the oxygen saturation curve or oxygen dissociation curve. The same thing, right shift and left shift is also explained by the same allosteric effector. Okay, do you have any other question? Do you have any other question, please? Because we have time, I have kept this slide very low because I want you to understand all these things. So please ask if you have any question. Or shall I call the name? I want to know who have understood me or not. Uzan Neopane, okay. Unmute your mic and ask me some question.
Yes, sir.
Soda ke question.
Sir, त्यो 2,3-डाइफस्फोग्लिसरेटको कन्सन्ट्रेसन टिस्युमा हाई हुँदा एटिपी जेनेरेसनमा के फरक पर्छ कि पर्दैन होला ग्लाइकोलाइसिसमा?
Normally के हुन्छ भने energy when there is excess of ATP, that time only 2,3 BPG is produced from the glycolytic pathway, okay, and that will be stored for some time in the tissue or in the RBC. When it binds to the hemoglobin, then what happens? The oxygen delivery will be very easy. So when there is high glucose only, that time this 2,3 BPG will be produced. Sabina, do you have any question?
Yeah.
Sabina?
No, sir.
Okay. Parul, do you have any question, Parul?
No, sir.
Parul?
No, sir.
Parul? You are not there? Okay. I think most of you have already left. Thank you so much. Bye-bye. See you in next class.
Thank you, sir.